Welcome to This Explainer. Okay, today we're embarking on a journey that is going to completely change how you view the universe. Seriously, we're diving into the invisible forces of the cosmos, specifically the absolutely fascinating world of magnetohydrodynamics. I know, it's a mouthful, but we're going to travel all the way from the microscopic interactions of superheated particles right up to the massive invisible planetary shields that literally protect our Earth from the violent extremes of space. Let's get into it.
You know, when you look up at the night sky, it's so easy to just assume that the vast blackness between the stars is, well, empty, just a perfect vacuum, right? Well, what if I told you that's actually completely wrong? The cosmos is actually filled with this highly conductive, really dynamic fluid. It's this swirling, electrified medium where magnetic fields and matter are locked in a constant, invisible dance. To really understand this fluid, we gotta define it. We are, of course, talking about plasma. So imagine a gas that's been heated to such an absolute extreme that its atoms are literally ripped apart. It becomes a fully ionized gas made up of positively charged protons and negatively charged electrons. Now, because these particles are charged, you might logically expect them to just violently repel or attract each other completely out of balance. But here's the secret of plasma. Strong electrostatic forces are constantly pulling those electrons and protons back into line. This ensures that, on a large scale anyway, the plasma remains perfectly electrically neutral.
So, here's our roadmap for today. We're going to start with the physics of plasma, move into frozen magnetic fields, then we'll scale things up to the solar wind, explore cosmic shockwaves, and finally look at Earth's magnetic shield.
Okay, Section 1. The physics of plasma and the microscopic rules of the universe. Let's dive right into this by focusing on the incredibly small scales where these foundational rules are actually written.
The absolutely crucial point here is understanding the difference between the microscopic and macroscopic behavior of plasma. Like we just talked about, plasma is neutral on a large scale. But zoom in to the microscopic scale, and tiny charge imbalances do actually happen. The maximum distance over which this imbalance can happen before the plasma, self-corrects, is called the Debye length. Think of it kind of like a microscopic shielding distance. If you drop a rogue positive charge into a plasma, the electrons will instantly swarm around it, literally like interplanetary paparazzi, shielding its electrical influence from the rest of the fluid. Now, beyond this tiny Debye length, that individual particle behavior completely disappears, and the macroscopic scale takes over. And on that vast scale, the plasma just acts as a single, unified, flowing fluid. Moving right along to Section 2. Frozen magnetic fields, and when plasma and magnetism lock together. Let's see how this builds into one of the absolute most fascinating phenomenon in astrophysics, all thanks to plasma's incredibly high electrical conductivity. Because cosmic plasmas are just so highly conductive, they show this crazy behavior called magnetic flux freezing. In a normal environment on Earth, you can move a magnet around without moving the air around it, right? But in a plasma with nearly infinite electrical conductivity, the magnetic field lines become physically locked or frozen into the fluid itself. What this means is that if the plasma moves, the magnetic field is dragged perfectly along with it. And it works the other way too. If the magnetic field shifts, the plasma is pulled right along for the ride. And just look at this. It brilliantly illustrates the concept. You can see these glowing coronal loops extending way high up above active sunspots on our sun. Now, normally, magnetic fields are completely invisible, but because of magnetic flux freezing, the superheated glowing plasma of the solar corona is trapped exactly along those magnetic field lines. The plasma is basically acting as visual proof here, tracing out the invisible architecture of the magnetic forces. Wherever those magnetic loops twist and arch, the plasma absolutely has to follow.
Let's apply this to a real astrophysical event to see just how wild this gets. Imagine a massive star coming to the end of its life, right? It collapses into a dense core known as a white dwarf. The star actually shrinks by a factor of 100 in radius. But because the magnetic field is frozen into the star's plasma, it can't escape during that collapse. As the star's surface area drastically shrinks down, those magnetic field lines get squeezed incredibly tightly together. The result? The magnetic field doesn't just survive the collapse, it amplifies exponentially. Shrinking by a factor of 100 leads to a magnetic field that is 10,000 times stronger. This perfectly explains the insanely intense magnetic fields we observe in dead stars like white dwarfs and neutron stars.
Okay, Section 3.
the solar wind, a supersonic cosmic outflow. Now we're going to scale up to our very own star to see where these frozen magnetic fields directly impact our entire solar system.
So, the solar wind, it's this steady, supersonic outflow of hot gas from the sun's corona. Let's break down exactly how it moves through space. Step 1. The sun is constantly rotating on its axis, doing a full turn about every 26 days. Step 2. While it's spinning, this incredibly hot plasma is just shooting straight outward in all directions at a staggering speed, roughly 350 kilometers per second. Now, remember flux freezing? Because the magnetic field is rooted in the rotating sun, but is also frozen into that plasma shooting outward, it creates this crazy twisting effect. That brings us to step 3. The magnetic fields are dragged into a massive, elegant spiral shape stretching all the way across the solar system. Actually, think of it a lot like water droplets spiraling out of a rotating garden sprinkler.
So how do we actually know this? Well, while the theoretical spiral is super elegant, data from the Ulysses spacecraft, which took measurements as it flew over the poles of the sun, revealed a much more chaotic reality. It turns out the wind blows much faster at the sun's poles, often hitting 800 kilometers per second, and it's quite a bit slower near the equator. Yet, all of that wind, fast or slow, carries that frozen magnetic field, effectively wrapping our entire solar system in a massive, supersonic magnetic cocoon.
Which brings us to Section 4, cosmic shockwaves, or breaking the sound barrier in space. You see, space is not some quiet, empty void. It is full of chaotic motion. And when these high-speed solar streams plow into slower mediums, we get cosmic shockwaves.
A shockwave happens when a disturbance travels faster than the speed of sound in that particular medium. Basically, the gas ahead has zero warning that something big is coming. When the supersonic flow hits, it creates a sudden, violent discontinuity. Now, instead of getting bogged down in all the complex math here, I just want you to remember 3 simple rules that govern this violent collision. First, mass flux is conserved, meaning whatever mass goes into the shock has to come out. Second, energy flux remains continuous, so the kinetic energy of that fast-moving gas is suddenly converted into immense heat. And third, momentum flux is continuous, which means the pressure spikes dramatically. These 3 rules dictate exactly how cosmic gases are instantaneously heated and compressed.
If that sounds a little abstract, just think of a supersonic piston. If you drive a piston into a tube of gas way faster than the speed of sound, those gas molecules just don't have the time to gently move out of the way. They get violently slammed together. This creates a shock front that actually runs slightly ahead of the piston itself. We call that gap, the distance between the moving object and the actual shock front, the standoff distance. And the gas caught in that space, it is brutally squeezed, heated, and compressed.
And that brings us perfectly to our final chapter, Section 5, Earth's magnetic shield, the ultimate cosmic deflector. Right this second, our Earth is acting exactly like an obstacle in the path of that supersonic flow we just talked about. We are constantly being bombarded by the solar wind. So how are we surviving it?
Well, we survive thanks to the Earth's magnetosphere. Let me be your tour guide for a second here, because this is literally our ultimate cosmic deflector. Imagine the supersonic solar wind rushing toward us, but right before it can hit the Earth's atmosphere, it slams into our magnetic field, creating this massive bow shock, just exactly like the shockwave ahead of that supersonic piston we were just looking at. The solar wind is forced to flow completely around us, creating a boundary called the magnetopause. You can actually see how the pressure of the solar wind violently squashes our magnetic field on the sunward side, but physically drags and stretches it out on the night side into this massive elongated cylinder called the magnetotail, which trails far past the orbit of the moon.
But, this shield isn't completely impenetrable. Sometimes, way out in that long, stretched magnetotail, the magnetic field lines get so twisted that they actually break and reconnect, snapping violently like rubber bands. This rapidly accelerates trapped solar wind particles, shooting them right back toward Earth. They drift along the magnetic field lines, funneling directly down into our north and south poles. When these super high-energy particles smash into oxygen atoms in our upper atmosphere, they excite the atoms, causing them to emit these brilliant flashes of red and green light. So the big takeaway here is that the beautiful northern and southern lights, the aurora, are quite literally the glowing footprints of these massive, invisible plasma battles happening hundreds of thousands of miles away in our magnetotail.
It really makes you look at the sky differently, doesn't it? The universe isn't just an empty void. It is a dynamic canvas of charged particles, frozen magnetic fields, and supersonic shockwaves, all interacting in this incredibly intricate cosmic ballet. As we look up at the auroras and realize they're just a tiny visible fraction of the massive magnetohydrodynamic engine protecting our planet, it leaves us with a pretty profound question. What other invisible magnetic battles are shaping the distant, unseen corners of our universe right this very second? Thank you so much for joining me on this explainer. Keep wondering and keep looking up.